I think of the customary comment, so I'm in panic too.
No, this will not work. This one? Yeah, okay.
No, this one doesn't fit.
But
Carlos.
I already asked some people. How about, is it all PDF?
Okay, maybe.
Is
Oh, I
it
can
all-
send you order. It's up to you.
But is it all PDF? I can
send
just
it.
download it from the.
Okay, you can use PDF, of course. Are you
But
downloading?
I don't need to do anything for the remote participation.
Yeah, you do it.
I think we should start it probably. Good afternoon. This is Lwig. So if you're not here for Lwig, you may leave the room. Sorry for the delay. We were looking for adapter. Too live, right?
Unprepared, you mean?
Yeah. All right. So note well, the new note well. So I guess by now you're already familiar with the note well. We can just move ahead. Olaf has kindly agreed to be the Jabber scribe. We need a note taker. Is someone willing to take notes? Anyone willing to take notes? Okay, Rahul, thanks. So here's the working group status. We had two drafts that cleared the IETF last call and all the IESG comments, and they are now in the RFC queue. And the third draft is also in the RFC queue, but has a missing reference to SNML, so it will also move ahead at some point. We have a packed agenda for today, and now is the time for, if you don't agree with this agenda or want to add something, remove something. If not, we can start with the first presentation. I wonder if this works. Yes.
Okay, good afternoon, everyone. My name is Carlos Gomez. I'm going to present the last update of the draft entitled TCP Usage Guidance in the Internet of Things. Other authors of the document are John Crowcroft from the University of Cambridge and Michael Scharf from Nokia. So first of all, let's take a look at the status of the draft. So the draft became a working group document after IETF 99. And since the last IETF meeting in Singapore, we have revised the document. So the last revision is 02. And this last revision is intended to address the feedback that we received in Singapore. And in addition, we've also tried to better organize the sections that provide the actual guidance in this document, which correspond to current sections 4 and 5. So basically this part is mostly a reorganization of content and only just a small new subsection for these sections 4 and 5. Okay, so let's go through the updates in this last revision. So our first update is in section 1, introduction, which is a new paragraph, some text intended to address a comment by Hannes in Singapore on which are the reasons for why TCP is perceived as a not so good or a bad protocol for IoT scenarios. And we've also added a reference to a more detailed document on this topic. So among the reasons that we include in this short summary, we can find that some of them are possibly valid. However, we believe that some others, basically the stronger ones, are possibly invalid reasons. So valid reasons for criticizing TCP as a protocol for IoT comprise at least the following. First of all, TCP has a relatively long header size, at least if you compare this, for example, with the header size of other protocols such as UDP. And in fact, in some scenarios, the situation is a bit worse for TCP because there is no, for example, 6LoWPAN style header compression defined for TCP. Then TCP being a unicast protocol is not suitable for multicast, while multicast is important in some IoT applications. And also, TCP provides an always confirmed data delivery service. So, for example, you may compare with what happens in CoAP, where you may, well, a sender may may choose whether an acknowledgement is required for a message or not. And this is some flexibility that can be useful for some scenarios and applications, especially for applications where you can tolerate some loss ratio, and you can just skip waiting for an acknowledgement, and by that you can get some energy savings for energy constrained devices. However, for TCP, this flexibility does not exist. And on the other hand, there have been many typical reasons for criticizing TCP, which we believe are invalid or are not fair. One of the most typical ones is the complexity of TCP. So it is true that there are many mechanisms defined for TCP. However, it's true also that much of the functionality is optional. So it is not really required, all that functionality for interoperability. And in fact, it's possible to implement TCP in a quite simple way. For example, by having a single MSS window size oriented implementation. Then, secondly, another claim that appears sometimes in the literature is that the connection-oriented approach of TCP is incompatible with radio duty cycling. So the latter is a technique that's quite typically used in wireless low power technologies for devices that are energy constrained, and it is based on having the constrained device in sleep mode during some intervals, or maybe by default and waking up sometimes for communication. And the point is that there is not any actual problem with having the constrained device in sleep mode for some intervals, okay? While the device is in a TCP connection. So the consequence that there will be when there's radio duty cycling in place is that sometimes to deliver data to the sleepy device, there will be some additional delay. However, if radio duty cycling is suitably configured, there is not any further problem than that. So, for example, when the device goes to sleep, it does not necessarily break the connection. And another claim or another reason for criticizing TCP is actually a bit more general and well-known for quite some time about underperformance of TCP in wireless links, for example. So it is true that TCP activates congestion control mechanisms whenever there's a packet loss. And the problem is that sometimes packet losses will happen not due to congestion, but due to corruption in, for example, high bit error links, which are quite typical in IoT scenarios. So the problem here is that TCP behaves quite conservatively, assuming that any loss is due to congestion, and therefore there will be this underperformance. However, the main point here is that this problem is not specific of TCP. So the actual problem is the fact that the transport layer protocol doesn't know which is the reason for a packet loss. So this is a problem that will happen also in other protocols. For example, in CoAP, there's the same issue. However, I'm not aware of any claim against CoAP being a bad protocol for the IoT. So we believe these are some of the main typical claims against TCP for IoT, which, however, we believe are not valid or not fair. Okay, then we have a quite major update in former section 4, which was entitled TCP over constrained node networks. The update is mostly editorial and relates with how we organize the content. So basically now the content is split in 2 sections. The first one is now entitled TCP implementation and configuration in constrained node networks, while there's section 5, which is entitled TCP usage recommendations in constrained node networks. So the last section deals with how an application will use or handle connections in constrained node network environments. And the previous one, section 4, is divided in 3 subsections. The first one, 4.1, is focuses on path properties. So it focuses on parameters and mechanisms that are related with path properties. Then 4.2 focuses on guidance for implementations which are based on single MSS window size. And 4.3 provides guidance for implementations for devices that can afford somewhat larger window sizes. By the way, there's the only actual update in terms of content here is the small subsection 5.3 entitled number of parallel connections. So basically we just say that a device that has limited resources needs to keep a low number of parallel connections, since each one of them, each connection will consume some resources. Then we have some other updates in the annex of the document, which is the part where we collect details on TCP implementations for constrained devices. So first couple of updates is in the subsection on the TCP implementation for Tiny OS. So we now have added that this implementation provides a subset of the socket interface. So there was a comment by Rahul in Singapore on this. And also we found that it appears that this implementation supports also multiple TCP connections in parallel. Then we've also added details for 2 additional TCP implementations for constrained devices. This is basically after some comments by Hannes in Singapore that, well, we've added the implementations for FreeRTOS and for microC OS. So these 2 are real-time operating systems for embedded devices, which are supported by up to 32-bit microprocessors. So now we are covering implementations for a bit more powerful platforms than the ones we were covering in the previous version of the document. And both basically are based on a multiple MSS window size, although FreeRTOS has some readily available option called Tiny TCP to quickly or easily configure it as a single MSS implementation. Also, both implementations support delayed acknowledgements, and there's one particular detail in FreeRTOS implementation because the threshold of the delayed acknowledgements mechanism is set to 20 milliseconds instead of the typical value of 200 milliseconds. And this is intended to gain performance by reducing delay in interactions that just require a single segment in order to transfer some payload. Then we've also updated the summary table that collects the different features of these different TCP implementations that we have considered in the document. So first of all, we can say that there are 2 rows that have been deleted from the table. Those were the rows for TFO and ECN, because actually there was a no everywhere. So now the same information is provided as one sentence in the table caption. And on the other hand, we have added two rows, one for whether there is support for the socket interface, and another one on the number of, well, whether it's possible to have a number of concurrent connections. Then also we have added the two columns that correspond to the details of the implementations for FreeRTOS and MicroC OS. And basically the part of the table that deals with TCP features is almost complete, although as you can see, there are still a few details that need to be filled in. However, we are struggling a bit more with details, numbers on memory consumption. So especially data size is something that appears to be not so easy to find. And for the code size part, we have found some numbers. And by the way, now in this last update, we've also added for each of these numbers, whether they correspond to just the TCP part or to the whole protocol stack. There was a comment by Mohit on this. And I'd like to take the opportunity to also make a call so that if anyone has details on this, especially for memory consumption and data size for the different TCP implementations, please let us know. This would be much appreciated. So then those were all the updates or the main updates in this last revision. And we have identified a number of potential additions for 03. For example, we plan to add some discussion on the support or lack of support of ECN in the internet and also in more specifically IoT scenarios. Then with regard to the security consideration section, we'd like to possibly expand it. And one thing we are interested would be to know if there are any known code vulnerabilities due to implementing TCP in a constrained way. So this is something that's a question that we also would like to make to the working group right now, for example, and also we plan to maybe post an email on the mailing list on this. And then in the annex, we also plan to maybe separate which are the TCP implementations that appear to be updated and maintained recently from those that have not been updated or maintained since some time ago. And well, and again, it would be great to try to complete the summary table. However, we believe we may need some help in terms of data and code size details. So any input in this regard is very much welcome. And yeah, that was the last slide. So I don't know if there may be any comments or questions.
Suresh Krishnan. So I had a specific question about the appendix, like I think it's 8, section 8, right? One of the things that worries me is like that's like highly dynamic content. And I had a thought, like just like run it, I want to run it by the working group, see what they think, right? So usually this kind of stuff is tracked in something called an implementation status section that's removed before publication as an RFC, okay? So that's like RFC 7932 or something like that. It describes how we do it. And that's how it's usually been done. So I want to understand if the working group thinks there's like long-term archival value for keeping this, or is something we just do this now and be done with it. So that would determine like whether you want to put it in an implementation status section or keep it in the RFC. Because I think an RFC giving wrong information is worse than not having the information. But maybe people may feel otherwise. It's maybe just a snapshot or something. But I think Hannes wants to say something. But yeah, just think about it. Like, what do you want to do?
Serge, are you specifically referring to the ECN support or the table that was previously shown, or to some of the performance data?
Implementation details, like it is,
Yeah.
like this OS does these things right now.
Yeah. Of course, these things change, but I thought that this table was at least it could be a snapshot in time. It would. I think this is quite valuable. I saw that that was really useful. Of course, it's a fair comment on like how do we actually maintain this? Could just be updated in a few years.
Think
Or so.
about like what will go
Yeah.
and I'm okay either way.
I understand that it's very difficult to get the data about data size and code size. But since there are lots of people in the room who always focus on code size, RAM utilization over the wire transmission size, I think it would be a a good exercise to actually get some real data. If you get the data from some papers, I expect that this will be tricky because they will probably measure it differently. They will probably include different values. And so you will have a not very representative figure in the end. So that could be, but I understand that you as the authors of the document, you're probably not super thrilled about the idea that you have to get all these things running and then do a comparison for the code size. It may not be the ultimate issue, but it would still take you some time. But for the RAM size, even measuring that will be tricky. I'm sure you have noticed that.
Yeah, this is Mohit. So I think I agree with Hannes that it makes sense to have these numbers and not remove them before publication. Yeah, once it is RFC, so we just update it. We don't remove it, but we keep updating the curves, right? So today is this elliptic curve, tomorrow it's some other curve, and things will change. But it makes sense to have like at this point of time, this is what we know. These are the numbers. And of course, measuring RAM is much harder because you either run the code or you use analyzer, and both of them don't give you accurate values, and they use so many different languages that it's hard to do that. So RAM is.
There are ways to measure the RAM utilization, of course, and to get some real data without being overly intrusive. But it will require a sophisticated setup. So I've seen tools. In fact, I wanted to use a tool myself. Without making advertisement, it's actually not an ARM product either. So it's a company, an Austrian company, Percipio, who provides an analyzer, and they basically give all sorts of data. If you increment the code, then you can retrieve it from the board. Then, but I haven't used it myself. I want to play with it, see how easy it is. Maybe that could help.
Thank you.
I don't know if you say that already, but maybe you want to, at the beginning of the section, you just want to indicate that, so just a disclaimer that this was work done at the time of writing of this document,
Yes.
and may be incorrect at the time when the people read it. And
Yes.
then later on, I don't expect these implementations to change like on a daily basis. So maybe in a few years, then things could be revisited. And like you guys do, or Carsten does at least, try to redefine the classes and be more descriptive after a couple of years of experience. I could see that following similar lines, or as we do for crypto as well.
Thank you.
Rahul Jadhav. So regarding the question of implementations getting changed. So one point is that I think these are all the design aspects. So the implementations might change at a different level, but these things will remain same. For example, I don't see why UIP or Riot will support slow start or any congestion control algorithm in the future, and LWIP already supports it. So these are something fundamentally different. So I feel this table and some of the information which is already there in the draft should definitely be there.
Thank you.
Yeah, Suresh Krishnan. So I'm not sure I agree, right? Like, so the thing is, like, a lot of these no's could change into AS at some point, right? Like, so that's the part I'm concerned about, that we're giving misleading information, right? The code number probably won't change by March, or like yeses are probably not going to become no's at some point, right? But there's some stuff we say like no, but at some point people will implement it. Like if something becomes important, like, you know, delayed acts, for example, right? If somebody could just do it, like they just haven't done it. And so as long as there's some kind of disclaimer which says it's like a snapshot, which doesn't exist by now, right now, but you can put it something saying like, okay, like just like not a section, just actually move it into an actual appendix, even though it says appendix, it's in the actual body of the document. So push it somewhere further down and say like, this is a snapshot at the time of writing and may or may not be accurate, and probably like put in a link to a URL where it's getting tracked. Okay, that could probably give you some kind of, so this is the information we're kind of trying to push into a working group wiki rather than a RFC, because it's, so a lot of the times we think like, is this going to be valid in 5 years? That's the kind of like test we do to see what goes in a wiki and what goes in an RFC. And I think something here is going to be wrong in 5 years, like just gut feel. I might be wrong, you might be wrong, right? But that's the thinking. So just put it somewhere and say, like, may not be up to date, and like, the current status for this is tracked at wherever, and then somebody maintains it, like could be a working group wiki.
Just a moment. I'm not sure if I heard you suggest what I was going to say. Let's have the cake and eat it too.
Yeah.
Okay. So this will be in the document. The same table will be on the wiki, and the table on the wiki will live and have the current. Yeah. Now, who volunteered for maintaining that wiki? Carlos.
Default volunteer.
All right. Thank you, Carlos. Rahul, I guess you are next.
Rahul Jadhav. So I'm going to just present the update for this particular draft. I'm not going to go into the details of what this draft is about. But at a very high level, the draft talks about how to manage neighbor cache entries when the density of the network or the density of the nodes in a specific area is much higher than what cache table is, the cache table size is. So the only update that has been done since the past revision is the security consideration. So there had been one discussion in the 6-ish which talked about maintaining untrusted neighbor entries for some time while the pledge joins the network, or in case of PANAG authentication, while the PANAG client joins the network. So this specific security consideration has been added into the document. Thanks to Melissa for citing this in context to 6-ish. And today, again, there was some discussion. Tomorrow, there is some more discussion in role, which is going to happen in this context, but not exactly the same. So the draft is not a standard stack document. It's an informational RFC. So we are not aiming to change anything in the signaling or messaging in this particular document. So the inputs from this document might in turn go to, I'm hoping it will result in some changes in the role. It might result in some changes in the role as well as in maybe 6-loop. So, some update about the implementation. So Contiki already has some part of the implementation of this, which allows the 6LR node to manage neighbor cache entries in a way such that, even if the 6LR gets bombarded with more and more number of entries, it will still be able to manage it. Right? Does not have this implementation as of now, and other operating systems also don't have this implementation. So what Contiki doesn't have currently, so we already have this implementation. It's a proprietary implementation. We are planning to add this support to Contiki and hopefully to write as well as a pull request. So what we have, what Contiki currently doesn't have is it doesn't have any key management protocol. Once it doesn't have any, if it doesn't have any key management protocol, I'm talking about not the Contiki NG, but the Contiki operating system, which is the older version. So it cannot distinguish between a neighbor cache entry which is authenticated and unauthenticated. So there's a difference there. So it doesn't handle that currently. So there is no time. So the update that we had done in the security consideration is that you have a different timer. You manage a reservation for unauthenticated entries in a certain way. You have timers for those unauthenticated entries in a certain way, so that it will reduce the impact of an attack. It will reduce an impact to the attack, but it might not be able to totally avoid it. So what are the next steps? So we plan to do this implementation in Contiki. We plan to align the Contiki implementation with the draft's proposition and do some performance test. So the performance test would be in terms of like how many times the network had to change its routing adjacencies, and how soon, how was the network convergence time impacted because of such an implementation. That's all. Any questions? Next steps would definitely require some reviewers of this for this document.
Mohit, so have you spoken to the Contiki folks? Like, one thing is editing the code in the forked implementation, but maybe they are also interested to then use this in future.
They are co-authors, and we had a lot of discussions. They are also co-authors in this particular draft, and we had a lot of discussions before. Thank you.
Hello. So in 6 days, this working group will get 7 years old. Yeah, I cannot congratulate because it's still 6 days away. But I wish this working would have been around 11 or 12 years ago, because I wouldn't have to stand here now. So this is really a blast from the past. I, on the insistence of Thomas Swatain, documented something that I thought had been common knowledge for more than a decade now, but apparently hadn't. So it came up when when the 6-law working group built a 6-law fragmentation design team, and one of the objectives was to finally document this. So this is about memory efficient fragment forwarding with virtual reassembly buffers. Let me quickly talk about the standards this is based on, and you see from the standard number, this is really about something that's a decade, more than a decade old. Why we are doing this, how they work, and what we're going to do about this. So you know that RFC 4944 defines a link layer fragmentation or adaptation layer fragmentation, as I usually call it, mechanism. So we are able to take an IP packet, turn it into multiple adaptation layer fragments, and then hand them over to 802.15.4. And the fragmentation format is inspired from IPv4, so we have a datagram size and a datagram tag. And for any datagram that is not the first one, we also have a datagram offset as a unit of 8 bytes. So basically, you can think about this as a form of IP fragmentation that is undone at the place where the fragments are received. So when the packet leaves the 6LoWPAN domain, it's a whole packet still and not a lot of IP fragments, which would be much larger. Now, how do you implement fragmentation? You do it by providing reassembly buffers. So you build a reassembly buffer when you get the first fragment. Then you have something like a timeout while you're waiting for additional fragments to come in, and then well, either you reassemble it completely, then you can drop the reassembly buffer because you have processed it, or when you have a timeout, you drop it. And these timeouts have to be pretty long for a number of reasons. So usually they are dozens of seconds or even 60 seconds in some cases. So we're talking about buffers that are about 1 kilobyte that are reserved for 60 seconds and that are living on a constrained node. So this is really a bit of a hard proposition. RFC 6282, which redefined header compression, did not change anything about the fragmentation mechanism. So we are still using the same mechanism as in 4944. Now, what's the problem? Well, first of all, because our links are not particularly fast and media access may take some time, the idea of reassembling everything at every hop and then fragmenting it out again, that increases the latency. It essentially can double latency or more. And also the reliability. Well, fragmentation is bad for reliability in the first place. Don't do fragmentation, but we have to. But the bad thing is that the reliability is further negatively impacted by the fact that the forwarding nodes have limited memory. So if somebody starts to send a fragmented packet and somebody else starts to send a fragmented packet and a third sender starts to send a fragmented packet, we might run out of buffers and then the packet is gone. So it's much harder to actually deliver a fragmented packet than an unfragmented packet. So basically what we need to find is a way to actually get rid of the fragment in the forwarding node as quickly as possible. And that's known as fragment forwarding. So we actually want to send fragments onwards before we have received the whole packet. And that, of course, relieves the intermediate nodes of memory requirements. And the only one that really reassembles things is the final destination or the ABR, for instance, when the package is supposed to leave the 6-low-plane domain. Okay, so this is what we want to do. And again, I thought this had been common knowledge because it also had been documented in a book that is dated 2009. So that is getting 10 in a couple of months. We can actually emulate the function of a reassembly buffer. So we don't actually implement the reassembly buffer, we just act as if we had one. And that's called a virtual reassembly buffer. So real reassembly buffer is going to sit there and put the fragments together and then only when it's full actually starting to burst out fragments again. And the idea about the virtual reassembly buffer is that you just don't let the data sit here, you send them on as soon as you have enough information to actually do that. So in a virtual reassembly buffer environment, you essentially reduce the reassembly buffer to information that you need to identify the packet that you are working on, which is the layer 2 source and the datagram tag. And all the other information you just don't keep. You just send them out immediately when you get it. Of course, there's a little catch here. You have to have media access to send something. And while you're waiting for media access, you still make receiving packets. So you cannot count on getting rid of your fragments at the same speed that you receive them. So the reliability problem and requirement for buffer space remains. But in many cases, nodes will be able to actually get the media access in about the same speed in which they're receiving things. So the virtual reassembly buffer never actually stores actual data. And that's good because now suddenly we might keep 20 of them or something like that. It's no longer as costly because it's just a couple of bytes. So this figure, by the way, is from Thomas, who wrote another draft documenting virtual reassembly buffers. As I said, it's not always trivial to do this. For instance, you might have a situation in which the first fragment does not contain enough information to forward the packet. If you have a very long source route in your packet, you might have to wait for the first 2 fragments to come in before you know where that goes on. Or there might be out-of-order fragments. I think that's something that is to be discussed, how real these are in networks, but it might happen. And there's also a third problem, but that's a general problem about fragmentation. You do header compression hop by hop, and of course the packet looks different on every hop. And the layer 2 information that goes into the header compression with the packet also looks different on every hop. So the header compression will be slightly differently efficient on every hop. And if you do this naively, then you might get a packet that has a 128 byte fragment and a 50 byte fragment. And then you notice, oh, I need 129 bytes to represent the first fragment now because, yeah, it's something about the header compression became less efficient in this hop. For instance, the TTL changes, and there are only a few TTL sizes that we compress efficiently. So what do you do in that case? You actually send 3 fragments, 128, 1, and 50, and that doesn't make a lot of sense. There's a well understood trick. The original fragmenter doesn't send 128 and 50, it sends 50 and 128. So you have all the slack in the first fragment, and this means if you have to go from 50 to 51 or 55, that's not a problem. Yeah, security considerations, this is pretty much the same. It doesn't really change very much. So getting a node to start a reassembly buffer is as easy, but it's at least not as severe because we can have way more of these virtual reassembly buffers. And finally, we are not solving all the problems here. This is just an implementation trick. It's not a new protocol. So it cannot help us with the packet drop probability. It doesn't provide fragment recovery. It doesn't provide things like per fragment routing, which you may want to have. You cannot do saturation, sending fragments multiple times. Well, you can do it, but it doesn't really help as much as if you have a real special protocol for fragment recovery. So this is a completely different item, and this is out of scope for this group and is being looked at by Sixlo. So Sixlo has a fragmentation design team that was charged to produce 2 documents. One giving an overview of what we have. Originally the idea was to have that the information about the virtual reassembly buffer implementation technique in that document. But more importantly, this is also supposed to discuss it, analyze it, tell us how far does that take us. So it's supposed to have some numbers in it, some actual summary of research. So that's one thing the design team wants to do. And the other thing is get a standards track document out with a new protocol that adds fragment recovery. Okay, so how do we do this? As I said, Thomas wrote another document that also documented virtual reassembly buffers and a few other things, and that might become this document here. And yeah, it has a small section here about the VRB itself. It also has a section discussing it. So what are the limitations and so on, and we would add numbers there and so on. And that may continue to be a good topic for Sixlo because it's the forward-looking part, while my draft is the backward-looking part, documenting things that happened more than a decade ago. So yeah, the description was first published as draft Lwig. Thomas wrote another description, and after some back and forth and discussion, we came up with the idea to keep a document about the implementation technique in Lwig and put analysis and some analysis also of new protocol proposals, how they can avoid the limitations of the implementation technique into a Sixlo document, which will then be accompanied by one fragmentation recovery technique that is chosen by Sixlo. So that's where we want to go. Questions? Questions or comments?
Well, we have the Sixlo chair here, we have the AD here. I think this split makes sense, so sounds good to us as.
So I chair the design team. So we had this discussion this morning. I think we've had this like Lwig Sixlo question because it turns out we've published the same draft essentially within 24 hours. We didn't know of each other writing it. So there's no, you know, there's no conspiracy. There's no conspiracy. There's no, yeah. So what Carsten explained is exactly the plan, I think, if that works. So the pure implementation details, VRB, Lwig, Sixlo discusses that and the limits. We have some, Yach is working on simulation results where we show how the thing diverges and how for you know, 1/10 of the price in RAM memory, you actually get 100% reliability, stuff like this. And then the second Sixlo draft is about a new protocol. So makes perfect sense.
Yeah, Suresh Krishnan, so makes sense to me. So, and yeah, talk to Gabe and Samita as well, just so that they are like fully aware of it as well. And I don't see an issue, and at some point we might probably do a joint last call for both the working
Yes.
groups for both the documents. That's probably it.
Yes, I just want to say that Karsten and Thomas spoke with us, 6 low chairs, and we are okay with the plan. And also Suresh just reminded that it will be last called and reviewed by both working groups. So it's fine. Thanks.
Thank you. Any technical comments on this whole thing? I mean, is there anything else that should be documented about this? Who has implemented this? Okay.
That's one. That's one.
Oh, okay. Thank you.
All right. Thank you, Karsten. Next, we have a remote presentation from Rene. Rene, can you hear us?
Sorry, Juan Carlos, did you register him as a remote presenter for Miteco?
Yes.
Okay, so then he should just be able to get.
Yeah, Rene,
Otherwise, if he
So I don't
requests
have
the
no
line,
handles here, right?
sorry?
I don't have handles.
Yes.
Otherwise, he can just request the line and then you press the red button.
Rene, can you request the line? Then we can start with the last one and come back to Rene. Rene, you need to request access, so there's nothing we can do from here. You can maybe send him a email. Maybe we can go on to the next presentation and then come back to Rene. Rene, please send us an email or something. Sorry. Oh.
Hi, I'm Francesca Palombini. I'm going to present an update to the comparison of co-op security protocols. So this document was started last year in March. It was first presented in core, and then at last IETF it was presented in Lwig. So the update for this document. So we removed the RASA 6 low compressed DTLS from the document as suggested by Hannes. We aligned to update it to DTLS 1.3, so it's now version 26. It's much smaller header in DTLS 1.3, and also we added the short header format. We corrected some errors that were in the document, such as the legacy version number that was 0301, and the correct number is 0303. That doesn't change the overhead, but it was a mistake, so that's fixed. We added encrypted content type in both for TLS 1.3 and DTLS 1.3. we removed the nonce from TLS 1.3, and we added the consideration about GHC, which increases the overhead for TLS 1.3 and the TLS 1.3. So all these changes, you can check. The examples are very detailed, and yeah, then they implement these changes. So we also added a table with the overhead without MAC, as Karsten suggested during last meeting. And finally, we updated all the tables according to the updates and the summary. So this is the main body table of content. So we have now a section for DTLS 1.2 with and without GHC and connection ID, and a combination of those. Same for DTLS 1.3, including short header format. Then TLS 1.2, TLS 1.3 version 27, with and without GHC again, and then OSCORE version 11, which is the last one. This is a summary. So this is the table from the document with the updated numbers. So in green are numbers that are lower than the last version of the document. Then in light blue are the new numbers, so the numbers that we added for this version. And in red, those that are higher than the last document. So, yeah. This is the new table that we added. So this is just for the overhead without the MAC, while the table before is a function of how long the sequence number is, and it includes the okay, now I'm gonna finish. And it includes the MAC. So this is without the MAC for all the protocols, with and without GHC. Again, green is for lower number than before, and this is because of we updated according to updates in the document and fixed a few mistakes. So we are wondering what are the next steps for this document. It got support at IETF 100 and got support before when it was presented in core as well. So we think this document is ready to be adopted by the working group.
So this would be a point where we ask how many have read the document. All right. So, is there any objection to adopting this? There was clear interest at the last IETF, unless there is someone who thinks otherwise. I think we are. Yeah, we'll of course confirm it on the mailing list, but. Let's do a hum. So those who are for adoption of this draft, please hum now. Those who object to adoption of this draft, please hum now. Yeah, it's pretty clear. We'll confirm it on the list. Thanks, Francesca.
Thank you.
Let's hope it works with Renee now. Just press it.
Does it work now?
Yes, just Renee, just keep saying next slide and I will switch the slides.
Okay. Well, thanks very much, and thanks for giving me the opportunity to be remote. So this draft I submitted, I think in November or something like that, after email discussion with Moet. And it's about how to squeeze as much crypto on small devices as possible. And there are some simple suggestions, and those are on these slides. So one remark, the draft is like 12 pages, of which probably 11 pages are appendix, and there's only one page with just the description. But nevertheless, I managed to make 15 slides. But most of these slides are just things to glimpse over and just to get an appreciation for some problems and hopefully a solution direction. Next slide, please. Can you hear me?
Yes, go ahead.
Okay, sorry. So So currently in IETF we have quite some interest in implementing ECC on all kind of devices. It's in TLS 1.3 and it's in lots of IoT style devices. And I will just sketch the kind of the algorithm zoo that has evolved over time, and what to do with it if we want to cram as much on one device as possible. So I will go over the NIST curves, which have been there for at least 1.5 decades, I think, and some more recent curves suggested via the CFRG process, both for key agreement and for signature schemes. And then I will zoom in a little bit. So I have a few slides with mathematical detail, but you don't have to learn it by heart. Then I will just do a comparison where the implementation pitfalls lie, and then I will suggest an approach on how to actually still cram as much on one device as possible. Suppose you want to implement more than one algorithm. So that's the precursor is really you have to implement for whatever reason. Let's say you deal with the US government, you have to implement the PTIF 56 curve with ECDSA, but you also want to use all these nice things that came out of the CFRG group. And then I will also sketch, once I've suggested how to reuse some code to implement all of these schemes on basically one implementation. I'll sketch like how can we evolve from here and can we make potentially our standardization process somewhat easier. So my kind of hidden claim is that lots of documents that have been produced in crypto land in IETF the last few years, they could have been one-page documents if they had a document that I submitted in November. And then I will conclude with some final remarks. Next slide, please. Okay, so this is the NIST curves, and the most important thing is there's lots of detail on these slides, but there is an overview on a few slides down the road. These are widely implemented. There's lots of hardware implementations for this. It's all over the place. The important thing to notice is that they use a particular shape of elliptic curves, which is so-called the Weierstrass model. And you see this equation, the curve equation, with the mod p and the x and y parameters on there. And this particular shape of equation, it triggers all kinds of other design decisions, including how do you do so-called group operations on this curve, how do you represent points, and so on. So lots of standardization bodies have picked some choices. So one I just want to highlight is that the points are always submitted in most significant bit and octet order, and that these objects that are on this curve are always in so-called non-compressed form. So it means you have all the information that you need to run a calculation. It's not something that you have to magically reconstruct. Then we have ECDSA. It's all over the place as well. It's a signature scheme. There we use the same elliptic curve as, for example, has been specified by NIST. We use a hash function, and then we pop out a signature of, in this case, 512 bits, again in a particular format. So this is just basically legacy curves, has been around since probably around 2000. Okay, next slide, please. So now comes CFRG, and they have introduced some new curves, so not that new anymore, but at most 2 years old in terms of spec work. One of them is a Montgomery curve, and that's a well-known curve 25519 that has been heavily promoted by Bernstein and some others. And that curve has been picked in a particular way, both to make the calculations a little bit speedier, and because of at least lately suspicions that the NIST numbers were cooked up. So one important remark there is that some of the speed ups actually may work less well in an IoT setting. So for example, on an Atmega 320p device, 328p device, Most multiplications you do are on the 8-bit level, and all the papers that are written in academia about speed records are all about 32-bit or 64-bit architectures, which is nice for TLS, but maybe not nice for every IoT application. So one thing to note here would be that the calculations are done on only one of the X and Y coordinates of the points there. So you basically throw away information, so you don't really reconstruct the entire thing that you would otherwise need in the Weierstrass form in the NIST curve case, but it still is enough for lots of key agreement protocols. Next slide, please. Okay, so then we have another type of curve, which is being used in CRVG spec for a new signature scheme called ED-DSA. And that uses yet another form of elliptic curve. It's called the twisted adverse curve. And there use yet another set of formula to hit speed records and to be the fastest in the world, right? And that particular representation has been used in a paper that later on formed the basis for RFC 8032 for the so-called Schnorr signature scheme, and it's operated in a deterministic fashion using all kind of SHA-512 and in other cases even more exotic hash functions. But you see, there's lots of flavors of curves. So let me just give an overview of them, and that's on the next slide. Can we go to the next slide? Okay, so I just walked over these three different curve models. So one, the NIST curves, Weierstrass model, the curve 25519 is Montgomery curve, adverse curve. They all have different underlying formulas under the hood of how to do group operations. They have different representations of how the points are represented internally and also how they are sent over the wire. And they even have different bit and byte orderings. So for example, if you look at the left column is under NIST P256, you see that the octets are sent, let's say, normal elementary school order, and same with bits. And with curve 25509, then the octets are least significant byte first, but on the octet level it's the other way around, and the adverse curve does something yet completely different. So what are we going to do now if we want to implement or have to implement, for example, NIST curves and NIST signature schemes, and we also want to use the CRVG stuff on a small device? So that seems to be quite a pain, right? Because all even the formatting is different, like the bit octet ordering, the underlying formulas are different, arithmetic is different. So it seems like, oh, we need to have triple the implementation size or the sum of the implementation sizes of the individual components, which is bad news for IoT devices. So let's see how we can make sense of this. Maybe we can actually do better. So that's the next slide, or next 6 slides, I think. Can we go to the next slide?
We are on the next slide.
Oh, sorry. Can we go back then? I didn't see it on my screen. Okay, so I just recopied the comparison of all these curves. And for now, I want to ignore the bit byte ordering because it's kind of a mess, but it's only a slim layer to convert one to the other. So let's focus on the elliptic curve crypto at first. So to make the exposition a little bit clearer, I assume that all the information is there. We don't do anything compressed. So we have all the X and Y coordinates of all these different shapes of curves. And then we'll try to see whether we can actually magically turn this into something that looks like a NIST curve implementation. Next slide, please. Okay, so you see that I have a blue item there where it used to say NIST P256. And what is that? So we have this curve 25519 and this adverse curve. If you look at all these specs, you think that all these curves are completely different mathematical animals, but they're not. They're just different ways of representing the same mathematical objects. And it turns out that you're able to, with all these three curve models, once you actually have something like curve 25519, you can easily convert the point to something on a different representation, like an adverse curve, or the curve that I specified in my draft, which is something in the traditional Weierstrass format. And just for the record, like every curve can always be represented in Weierstrass format, but it's not always representable in Montgomery or adverse format. So you see this little diagram on the bottom. Essentially, we have a way to move between different representations of the same object. So these seemingly different things are just different way of representing the same mathematical objects. And these mappings between, for example, the curve 25519 and this new thing that I introduced in the spec, in the draft, these are very easy to implement. So let's look at it on the next slide. So here if you just first focus on the bottom. So we have a curve 25519 point, which is people are using it in IoT applications. It has two coordinates, u and v. X and y. You have to look at the red arrow going to the left. How do you move towards something that looks like a NIST Weierstrass format? You just add some number to the x coordinate. That's it. Same thing. If you want to move the other way around, you just subtract a number. That's it. So the computational workload of moving from one to the other direction is 0.1% at most, maybe even far less, right? Something similar happens if you move between this adverse curve and the curve 25519. So that means, for example, if you can do this very efficiently, you can have a single implementation for the signature scheme that came out of CRG and this extra 25519 implementation, as long as you convert it to the other format. And then at the end of the computation, just convert it back. And the reason why this works is that it's a so-called isomorphism, which means that you maintain the same mathematical structure. So now we have essentially three representation of the same mathematical object. One of them is the curve 25519, the adverse curve that's in the EDDZ scheme, and the thing I specified in the draft. And they all have the same parameters. They have the same prime number, so you can just borrow all the arithmetic for it. Same group size. The only thing is like the representation, the XY coordinates are morphed a little bit. So, for example, in curve 25519, you have an x-coordinate 9 as the so-called base point, but it's 9 plus a fixed number that is a little bit long to write on the slide, but it's nevertheless a simple add, an integer add. That transforms it to the other format. So the important lesson from this slide and the previous few slides is that we have all these seemingly different objects that essentially are the same, except they are representing their coordinates slightly differently. And we want to exploit that to essentially stick it into an existing hardware implementation for example, the NIST curves. Next slide, please. So now I have, I condensed all these different new improved curves to just this one in Weierstrass format. And we now see that if we compare it with the NIST curve that has been around forever, and it's like probably hundreds of hardware implementations for that already available. We have the same curve model, we have the same base point now, we have the same internal representation, the same formula, the same wire format, and the same octet ordering and bit ordering. So that means that if suppose you're kind of late in the game and only want to start implementing the Montgomery curve or the adverse curve now, maybe you can just transform it to Weierstrass format, dust off an old hardware implementation for the NIST curves, and you're done. The only thing you need to do is you represent it in a different way, and you use other so-called domain parameters. So if the NIST curve uses another prime number than the other curves, and a few other parameters, but these are constant and they're easily loaded into memory. Okay, next slide, please. So I cheated a little bit because we also actually had all these encoding problems because the bit and byte ordering in all these different models has been picked kind of badly because they're all like incompatible. So if you really want to implement all these different models in the same way, we need to at least solve this encoding mess. So if the octet ordering was least significant byte first instead of most significant byte first, we have to have a little translation layer there. So apart from that issue, we can implement all these things in the same way. And we can, if we, for whatever reason, we already have kind of a classical Weierstrass curve implementation, we can implement all these things also in the same way. Next slide, please, with some efficiency. So what is the efficiency of this whole exercise? So one advantage, of course, is, we only need one implementation instead of all these flavors, except for the little bit byte ordering mess. The conversion is really low cost. As I said in the first bullet, it's like really negligible. There's one caveat, though, is that if you look, for example, TLS, I saw today that TLS 1.3 was just approved. And TLS 1.3 uses this curve 25519, and for reasons that I really don't understand, they only format the x-coordinate of the point instead of both coordinates, which handicaps my mapping between these curve formats, because now suddenly we have to recompute those things. So if TLS 1.3 had thought a little bit more about the representation issues, then this 0.1% would be the final cost. But because they didn't do that, now we have a very expensive calculation we have to add to transfer to this Weierstrass format or Atlas format, which adds roughly 1/7 of the total scalar multiplication time. And then all the bit and byte orderings, they cause a little bit of complication, but it's only an ordering of octets, so it's a pain that should have been avoided if we look back now. But it's there, and it's at least computational cost is quite low, right? Okay, so next slide. I only have like 2 slides to go. So how to reuse existing steps, right? So suppose we have to implement the NIST curve with a key agreement and curve 25519 in TLS 1.3. And we want to do it on a small device. Then under the hood, we can just do Diffie-Hellman with this curve I specified in the draft. And then we're even compliant with existing NIST specification. We get all the compliance stamps. We get all like FIPS approved and so on. They already announced that they would give you the stamp November last year. If you want to do key agreement and signing using the CFIG curves, then we can also, if we want to, for whatever reason, do the Weierstrass model, we can already do that. And I actually checked all the specs. If you look at FIPS 186-4, it allows specifications of all kind of curves. So it does allow introduction of a new Weierstrass curve, which is, for example, the one I specified in the draft. And then we have ECDSA suddenly with a curve that under the hood you can just do the calculation with the Montgomery ladder, like CFG has been promoting. And it's compliant. And NIST doesn't have to do their 3-year rewrite, and it can all be done. If you want to implement the SNOR signature scheme, which is essentially EDDSA, we can dust off the BSI spec of 2010. And it also allows new curves, although it recommends their own slow one. So we can do a fast one instead. And then we're done. Same with combination of any NIST and any CFG flavor curves. As long as we keep the same encoding, so most significant byte and bit first, then we don't have to do change any line of code of any existing specifications. There's one note in the bottom of the page is that if we want to reuse the ECDSA, and suppose you have an existing ECDSA implementation with NIST, and you want to use it to implement the Atlas EDSA scheme, then part of it is possible because all the elliptic curve arithmetic will work just fine. The only thing is CFG has implemented SHA-512, so there's a mismatch on the hash function, so you have to implement 2 hash functions now. And the other thing is some of the formula under the hood is slightly different to compute the so-called S component of the signature. And you can still do it, but you cannot do it easily in a secure way. So you have to, in that way, you cannot exactly reuse the existing implementation, which was the premise of my whole presentation. So next slide. Okay, now suppose you want to do instead of rapid prototyping, we would like to do rapid standardization development. So I think the CFG process to pick the new curves, apart from all the infighting, it also took 2 years to do it. And there's like 50 different drafts that are all about do a new curve with HTTP, do a new curve with Jose, and whatever, right? If we actually would use the Weierstrass model, we only had to define a new object ID for the curve, and we would have been done. We could have introduced MQV, we could have introduced new certificate formats with one-line drafts instead of like 60 pages. We could have used implicit search that are now used for autonomous vehicles in the US Department of Transport, all by just swapping to the old-fashioned representation that has been around in all kind of specs for 15 years. Next slide, please. Last slide. So the bottom line is, first of all, mathematically, different curve models, they look different and hard to understand, but they can all be seen as one way of representing or the other way of representing the same so-called short Weierstrass model. If you use that model, then you can use all the existing implementations of NIST-type code. But also, if you represent it that way, even if under the hood you use a kind of a fancier model like Montgomery ladder and so on, you can your standard development becomes one-pagers. You just specify the parameters and you're done. Then the third and fourth things are a takeaway that the encoding formats like TLS, I think, has done kind of an hindsight, kind of a bad choice, but at some moment one gives up trying. About representing points, which effectively makes it harder to switch from one representation to the next, which I think is detrimental for algorithm agility and for implementation security. Because essentially it has picked a favorite, which in this case would be the Montgomery curve, and made it harder to shift to another way of representing the same object. So I think in the future, IETF should be more careful about their representation conventions and whether they kind of dig a moat around the solution instead of make it agnostic. Yeah, so there's one question I had that I didn't put on the slide is essentially if for low-cost devices we really want to have one implementation, maybe we should define some of these things in a way presented in the document, and it could be beneficial for IoT type settings. So that's a big question mark for me. And the question is whether people think it's of interest to them. Should I pop out another draft? People will think that would be of interest to implement it this way, and so on. The floor is yours.
Okay, Suresh Krishnan. Hello? Okay, Suresh Krishnan. So I read the draft. It had like 3 pages, but I couldn't figure out what was implementation guidance in there. And I have a hard time seeing how this fits in Lwig, right? Like it's, and if you look at the appendix, it's like very crypto heavy. You want to swap batteries?
You mean the slides are crypto heavy or the draft? Both probably, right?
Right. The slides are, and I'm just worried that like we don't have the expertise in this group to review the crypto and vet it, right? Like, so if your strategy is going to be go with this stuff somewhere, I would like a different content in the draft which says like how this can be used in constrained implementations, right? And that's not the direction the draft is taking today, right? It says like,
well, so currently, if you look at the security consideration section, it says, we essentially define a mapping,
right,
that transform one representation into another one, which is public information. So there's no security impact. So there's no need for crypto people to do their own, pick their favorite things. This is for lightweight implementations. People can define a different way of representing things and may be able to reuse, for example, all the NIST-related code to define something where under the hood you would actually implement the CRG curves and signature schemes, right? So that's the only point is like if you only have to make, so right now everything that TLS has been doing, or TLS, IETF, is creating as much of a strong divide between the different curves types. And what I think would have been better in hindsight would be like, essentially we give all this flexibility. If under the hood you want to do Montgomery ladder, go ahead. If you want to do network curve, go ahead. If you want to reuse NIST hardware that has been all FIPS certified because you need it for your customers or whatever, go ahead, right? We could use the same ordering. So essentially, if you want to do a lightweight implementation, then this would be one approach of doing it, right?
Right. Like,
so all the appendices, the 10 pages of appendices in a draft are essentially tutorial for people who may not be into some of the crypto stuff. But the only thing that's essentially defined is an Annex D, which is the parameter sets and how they relate.
Right. Like, I think the part that's like kind of lacking in the draft is like, what to do, really, right? So I think we can probably take this up on the list, right? But for me, just reading like the content of the draft, it wasn't clear what it's asked is for the implementers of these, what's the guidance? It's not clear. So maybe maybe we can iterate on the list to figure out what that is. But I think that's the part that requires development.
Okay.
John Mattsson, Ericsson. First, great slides. I think this is an excellent reference for summarizing up all these standards. Then you said that, talked about governments. NIST has now stated that they plan to standardize curve 25519. So in the future, we might need to have a different terminology than NIST curves. Then one of the benefits with curve 25519 and Edwards 25519 is performance. What I'm lacking in this draft is what performance do you get when you use the bias version of 25519? What performance do you get when you do key generation, Diffie-Hellman function, and ECDSA with bias 25519 compared to EDDSA or curve 25519?
Yeah. I can give. I did some calculation, and it depends on some details. So we can talk about naive implementations, and then I think the Weierstrass curves they have roughly they take a 15 to 20% hit compared to curve 25519, and it could be more, but not on IoT devices. So on IoT devices, you cannot exploit all these fancy tricks that have been done. There's like a million new curves have been generated in academic literature the last 10 years. And they all do something like multiplication without a carry, right? But all these things don't really fit too much on lots of small platforms. Maybe on a 32-bit word size, but if it's less than that, it doesn't fit. So the only thing you can really gain is that your formula contains a fewer multiplications. So if that's the case, then the ratio is roughly, you may run a little bit slower, but not that much, less than 20%. If we talk about secure implementations, it depends a little bit on what you're interested in. So I look at the world as like ECC for extremely nasty environments. In my case, that's IoT devices. Then all these models have I've not seen any real implementation that actually meets those implementation security requirements. So it's hard to do a comparison, but the touted advantages of different curve models is far less than sometimes advertised. At least in highly hostile environments where you can do implementation attacks.
Thank you. Some information on this would be welcome in the new version of the draft, unless it's already.
It's hard to give implementation security related information, but I could definitely give some numbers about let's say the number of multipliers required in the Weierstraße versus the Montgomery and so on, right? Yeah.
Hi, René. This is Hannes. Thanks for that great work. I wasn't aware of it previously, so I forwarded it to my coworkers who are more sort of have that crypto expertise. We have obviously been facing that challenge with the implementations of the different curves, and so I think this is at the moment we haven't implemented all of them yet, so that's definitely a useful approach. Happy to work with you on sort of the performance characteristics and those things. I will definitely get in touch with you once I get the feedback from my coworkers.
Oh, that's great. Yeah.
Bob Moskowitz, HEG Consulting. Thank you, Renee, for this presentation and going through it. I really appreciate all I've learned from you and over the years on the math behind much of our crypto algorithms, and I recognize your expertise in this area. But there are other things to optimize than code use, and also if some code is better than other code. There's been much discussion of the aspects of the current P256 code base. Some is good, some is not good. What it takes to do, there's discussion on the EC25519 code base, comparing them. But there's also the difference, as you pointed out, in the XY representation of P256 versus EC2519 being only just the one axis. And I have specifically worked with one vendor on an 8-bit processor on a 32K memory allowance, and they just could not have done P256. The storage requirements and whatever else they were doing, that 32-byte made the difference for them, plus some of the other processing that I was able to get them to do the EC25519 implementation, and they tried. They could not do P256. So I specifically done this with one implementation. Of course, it varies across the map. And so when you're talking about optimization, there are many factors to consider on it. This is definitely one to consider and how you may be able to do things. But the best that Lwig can do is to, as you point out, is to tell TLS 13, can you please give a representation so that EC519 maps to the same as P256. Whether that has value or not, we can run down that path. But I really don't think when you take all the different optimization considerations in, that this is will get legs. But it's definitely very educational, and I really thank you, Renee.
Yeah, so this is not about provoking a choice, right?
Hi, Renee. So my name is Zintao, and getting out of math, I think there are some points that might be useful for many implementers of the the IoT world. I will also come back to ask our implementers to check if that's useful. Can we use some code and to break down the memory usage. But speaking as one of the co-chair of this working group, I really want this document to be focused on the detailed guidance for the things that in scope that will make I think this document more impactful and useful. That clear? And also, I think for the last item on the screen, which is some criticisms about the IETF, I think that's okay. I mean, that's happening every day. But I think that's probably you should talk this topic for this point. Maybe that's useful for the larger audience as out of scope of Lwig, probably the securities patch or some. I'm not sure right now, but I think we have space.
Yeah, I think this would definitely be useful to have more eyeballs on this, more than Lwig. Pretty much, but especially for this one, because this one we need all the crypto experts to have some say on this. But I think we are almost out of time, so maybe we look forward to your next version. One comment from Hannes.
So I guess the type of expertise that you need here is someone who implements a crypto library and also specifically, obviously, elliptic curve crypto and participates in the standards process, which of course is not the person you typically run into. So there may be in general like a limited number of people, and so we have to do some extra effort to reach out to those. Probably if we look around in a room, most of us are probably not the target audience for it, and so you could forget it right away. But that doesn't by itself make this document useless. I think it's on the other way, it's just a very complicated problem and complicated topic, and so I know within my company on who to talk to, and I'm sure you have similar guys in the company. So, but they typically don't sit around here. So, I think if we forward this presentation and the document to those people, I think we could get some useful input.
It's much appreciated.
All right, so we are adjourned for today. Thank you, everyone.